All right, hello and welcome back, everybody. We are at the whiteboard today because we are doing what I'm tentatively calling section, what were we on, 14.7. I'm going to name this section, the method of characteristics. So this is one of the classical methods that you would end up learning if you took more of a dedicated PDEs course. In many ways, this is an underlined method for solving first order linear PDEs. You recall the order of a PDE is the highest number of derivatives. And linear means that the only operations are multiplication and addition, and in both cases, those operations exist by independent functions, as in not multiplying an unknown with itself. So we're not allowed to take like u squared. If we're solving for the function u, we're not allowed to consider things like u squared, u cubed, square root of u. We can only ever add u to itself, or we can multiply by some independent function. So a nice example of this, for example, the PDE x plus t partial x u minus x squared plus 11xt partial t u equals 0 is a linear PDE first order because I only have one derivative on each term, and I'm only multiplying by independent functions. I'm not allowed to multiply by u. If, this is maybe a nice little example, if I put a u here, this term would be not linear. So we want to make sure that anything we're multiplying by is not the function we're trying to solve for. Okay, now, interestingly, the PDEs you've considered so far do not fall into this category because the PDEs you've been working with are second order PDEs. You've had the Laplacian in each one. And the Laplacian necessarily concerns second derivatives. So those were all second order, they were all linear. But they are not first order, which is why we are introducing the method of characteristics today. Because you can imagine first order PDEs are almost as ubiquitous as these second order ones you've been thinking of, because all this is saying is we can relate the velocity of some material to how it differs in space. So that seems like a pretty common thing to have, velocities changing depending on how something differs in space. Okay, so let's introduce the method of characteristics. So I'm just going to say, given the first order linear PDE, and this first order linear PDE, I'm going to restrict myself to one spatial dimension. We could increase our dimensions if we wanted to. Probably not for this course, though. You can take a PDEs course if it seems really interesting. So just in one spatial dimension, what does a generic first order linear PDE look like? Well, it's going to look something like f of x times partial derivative in x on u, g of t, it should be f of x and t, g of x and t, getting a train, function of x and t, partial t u is perhaps equal to a function of x and t times u, plus maybe even one more function of x and t, f, g, h, I. So that's kind of your generic first order linear PDE. The method comes down to, let's assume both x and t depend on a new variable, s, for example. Then x is really a function of s, and t is a function of s. Calculating a derivative in s of u of x, but now x is a function of a new variable, t is a function of a new variable. We recover, how do we take derivatives? This is something that maybe was not clear this semester, and I apologize for that, but how do we take derivatives of something like this? Well, we end up using the chain rule, right? This is basically a scalar field of a curve. This is jumping back to our chain rule of scalar field of a curve. So if we actually jump back to that section and compute everything out, what we would recover is partial u partial x dx ds plus partial u partial t dt ds. And I think that's going to be seem a little bit more familiar to all of you when we did our chain rules of scalar fields of curves. Well, the method of characteristics says, hey, let's compare these that I'm highlighting in yellow, because if they're equal, if these are equal, then the left-hand side of the PDE, as in this whole term, is d dt of u. So that's the method of characteristics in a nutshell. Let's see what making this assumption that dx ds is f of xt and dt ds is g of xt, let's see what making this assumption leads us. So if we make that assumption, I'm going to define that the assumption is true. So I'm going to define that dx ds equals f, and recall x is a function of s, t is a function of s. I'm going to define that the dt ds is equal to g, which is a function of s, a function of x, a function of s, t, a function of s. And under that definition, the whole thing in orange at the top of my screen happens to be du dt. So du dt is now equal to the right-hand side. I recover that du dt equals h x of s t of s on u plus I of x of s t of s. So what we recover under the method of characteristic is 3 ODEs. These are actually all ODEs, right? That's why I'm using the true derivative in s. This is my mistake, actually. This is dds there, duds there, duds up here, s there. So all 3 ordinary differential equations have shown up out of originally a partial differential equation. So the method of characteristics, you can think in a nutshell, is solving a system of ODEs instead of a PDE. So you have one PDE or you have a system of ODEs, because if we were able to solve this system, then we can actually convert our way back into the original solution to the PDE. Now that's as far as I'm going to go in defining this, because it's going to make a lot more sense in practice. So I'm just going to go through 2 examples, and then you'll see maybe why this is a little bit more useful of a method rather than just defining it, because it seems it's far too abstract in definition, I think, for you all to understand it completely. So let's just look at an example. And we'll do something like x partial x u plus x plus t partial x partial t u equals 0. This is definitely an ODE that you have not or a PDE that you have not yet learned how to solve. And yet you would think that you should be able to solve it, because it's not that tricky. You just have for first order in both directions, and you don't have linear multipliers, right? It's just the power of 1 in the multiplier. So it feels like something we should be able to solve, but we don't really have the tools yet until now we have method of characteristics. So step 1 is let x and t be functions of s, so hence xs ts. Step 2 is compute d ds of u under the assumption that the inputs of u actually depend on s now. And we're always going to recover partial u partial x dx ds plus partial u partial t du dt ds. We will always recover that in step 2. Step 3, we look back to our original equation and ask ourselves, oh, what were the multipliers of these particular terms in the original equation? And there they are. So step 3, construct the system, by making this identification that dx ds was equal to s. X. Dt ds is x plus t. And finally, the last term here is tricky. You kind of just have to remember that it is what it's supposed to be. That's du ds equals the right-hand side of the initial equation. So in this case, 0. So that is our system. And now we just solve it. And this is I know we haven't actually gone through solving systems of ODEs, but it should seem fairly straightforward. How do we solve this system? Because that doesn't care about t, that doesn't care about x or t. And so we can solve each of the terms in orange individually, and then we can work on the middle term. So solving the first one, dx ds equals x. Jumping back to first semester, I think you all recall that means that we have an exponential solution. So x of s is c1 e to the s. We necessarily have an exponential solution to this ODE. The u equation, du ds equals 0, that means that u is just a constant in s, right? And then we can solve the middle term here. Dt ds is x plus t, but we know what x is now. We know x is c1 e to the s plus t. If I go through the work on this, we would find out that the solution to this equation in t as a function of s is c1 s e to the s plus c2 e to the s. And so now we have x as a function of s and t as a function of s. And sorry, that was equal to 0, which means u equals a constant in s. Okay, so now we combine all three of these and we say u as a function of s is a constant, so then u in fact as a function of s and x and t, since those together make up the function of s, is still just a constant. And this is interesting, right? You'd be like, why did I go through all that work just to find out that u is a constant? Well, you didn't necessarily see that right away. It wasn't clear to see that u should necessarily be a constant from the beginning. But now that we go back to the beginning, if I look over here at my original equation in the top left, and I plug a constant in for u, you can imagine a derivative on a constant there is 0, a derivative on a constant there is 0, and so in fact we have solved our equation. So that's the method characteristics for an equation like this, which is maybe a little bit too trivial. Let's modify our equation just a little bit and see if we can get something non-trivial. Let's say that instead of being equal to a constant, on the right-hand side this was equal to t, for example. So let's say that that would modify my term right here, du ds, instead of being equal to 0, du ds is now equal to t. And I still have my full system. But now I had to work in terms. I know how to solve for x, I know how to solve for t, but now u is a little bit trickier. I have that du ds is t, but I know what t is from that. So now I have du ds is actually c1 s e to the s plus c2 e to the s. And all I have to do is integrate that to gain my solution. And when I integrate that, what I recover is that u of s is s c1 s minus 1 e to the s plus c2 e to the s. So now I have u as a function of s. I ask the question, can it be written as a function of x and t? So can I rewrite this function of s in terms of x and t? And the answer is yes. The answer will almost always be yes, but in this case it's yes because I'm a little bit clever. And I see that there's really a special t hiding in here, right? So t is c1s e to the s, and there's a c1s e to the s there, plus c2 e to the s, c2 e to the s there. And so there's actually a t hiding in there. The t is hiding in c1s and c2 e to the s. So there's a t from that term, and then in fact there's a -1 c1s. So -1 c1s is actually a minus x. And so we recover that there is a function of x and t that you can be written as, and all of a sudden we've actually solved our PDE. Should we verify? Let's verify that this actually solves the PDE. This is something a little bit more non-trivial for a PDE that we can solve. I guess I should say something at the bottom for step 4. So step 4 is, nice. Step 4 is rewrite u of s as u of x and t. And that's always the trickiest part. So I'll definitely help you all in class for that part. Rewriting u of s as u of x and t. But let's verify. Let's verify that this actually solves my ODE at the top. Let's compute partial x of u, the u at the bottom here. That gives me -1. Let's compute partial t of u at the bottom. I get 1. And so if I plug those values in here and here, I'm doing something like x times -1 plus x plus t times 1 equals, well, let's distribute that, -x plus t. The x's cancel, and I recover t like I was supposed to. So we have verified our solution. But yeah, this is definitely a non-trivial approach to these problems. It's a little bit cool when everything works out, but it's also a little bit tricky. So we'll definitely talk about this a lot in class. Anyway, that's all I have. Thanks for sticking with me. Bye.